All right, welcome ladies and gentlemen. This is video number 2 in our moles, reactions, and Stoich unit. So you need your notes open to the part where it says video number 2. This video is going to be about something called percent composition, which we have already talked about this year, so you should be a little familiar with. But we're going to be seeing this in the context of chemical formulas now, rather than percent composition of mixtures. So as an introduction and as a review a little bit of percent comp, imagine that you have a bucket with 125 pieces of fruit. If the bucket has 35 apples, 30 oranges, 20 pears, 40 bananas, what percentage of the bucket consists of bananas? Now this is something that I'm hoping that you kind of look at and you're like, well, yeah, I can figure that out. Because if you want the percent bananas, then you have to take your number of bananas, which is 40, and divide it by the total amount of fruit that's in your basket, which is 125, and then multiply it by 100. Because if you just divide the bananas by the fruit, you get a decimal, but percentage is taking that decimal and converting it into a number that's out of 100, so you're multiplying it by 100 at the end. So we're doing the 40 bananas right there, divided by the 125 total pieces of fruit right there, then multiplying it by 100, and we get 32%. Well, the absolutely lovely thing is that percent composition in terms of chemical formulas is no different at all from this idea of calculating the percentage fruit in this fruit basket. Percentage is always just part divided by whole. So the general formula for any percent is the part that you're interested in divided by the whole amount of the thing and then times 100. It's really important to include that times 100. That's what separates it from a decimal. That's what makes it a percentage. In terms of a chemical formula, in terms of the math of chemistry, the way we use percent is typically the percent by mass of each element that's in a compound. So the way that we can calculate that, it's still part over whole, but the part is the mass of the element in the compound, and the whole is the mass of the entire compound. So this is still part over whole times 100, but now our part is just, hey, how much of the element is in the compound, and then the whole is, what's the mass of the entire thing, and we are still multiplying it by 100 at the end. So as an example, a very common percent composition problem is what's the percent oxygen in potassium chlorate, KClO3. So in terms of the part and the whole, when we say the mass of the element and the mass of the whole entire compound, if there aren't specific masses in the problem, then you need the gram formula mass. Because the gram formula mass is going to be your whole, because that is going to be the mass of the entire compound. So the mass of the whole compound in this example is simply the GFM. So we're going to do 1 potassium, which is 39.1 grams per mole, plus a chlorine, which is 35.5 grams per mole, right? That's our K, that's our Cl. And then plus the 3 oxygens, so 3 times 16.0. 3 oxygens, and you add that together, and that's 122.6 grams per mole. Again, this is the whole. That's your whole thing, because that's the mass of the entire compound. And then if we want percent, then we need the mass of the part. Well, what's the part here? Well, it says, what is the percent oxygen, indicating that is the part that we are interested in this problem. So the mass of the part is the mass of the oxygen. So how do we determine the mass of the oxygen in this compound? Well, what's the mass of oxygen in terms of gram formula mass? That's 16.0, but there are 3 oxygens in the formula, as shown by the subscript 3, so we do have to take that into account. It's not just 1 16, there are 3 16s, and we get 48 grams per mole of the whole that's just oxygen. So then, determining the percent oxygen, it's the part of oxygen, which is 48, divided by the mass of the whole thing, which is 122.6 times 100, and we get 39.2%. The times 100 is absolutely critical. If you, quite often, a problem might simply ask for just what's the correct numerical setup for calculating the percent composition, and if you do not include the percent oxygen in your numerical setup, it is not a correct numerical setup. You have to include the times, you have to include the times 100. The times 100 is what makes it a percent. If you just do part over whole, that's not a percent. So somewhere in the problem, you must indicate that you are multiplying by 100. And then just one more example. What if the problem doesn't give us a chemical formula? How can we still determine the percent of an element in a problem? So if the problem gives you mass, use that instead of gram formula mass, because you can just use, if you don't have a gram formula mass, but you do have actual masses from a lab, then use that. So for an example here, a compound is formed when 9.03 grams of magnesium combines completely with 3.48 grams of nitrogen. What is the percent composition of this compound? So first of all, I want to address this last bit. What is the percent composition of this compound? Now, notice here that it doesn't ask for the percent of a specific element. If no element is specified, if it doesn't specify an element, you need to determine the percent of each element. Right? You need to calculate the percent of each one. So by asking for the percent composition of this compound, there are two elements in this compound, magnesium and nitrogen. I need the percent of each. So we need percent Mg and we need percent N. So percent is just part over whole. So if I want to start with the part, let's say the magnesium part, well, that's already been given to us, right? This right here, 9.03 grams of magnesium. This is our part that's magnesium. And this right here, the 3.48 grams of nitrogen, that's the part that's nitrogen. What we're missing is the whole in this problem. So how do we get the whole if the whole hasn't been supplied to us? Well, this compound only contains magnesium and nitrogen. So the compound is the magnesium plus the nitrogen. So we can simply add together the masses of the two to get the mass of the whole thing to be 12.51 grams. So the compound must weigh a total of 12.51 grams because it says it combines completely, and we know law of conservation of mass says that the mass of the products must be equal to the mass of the reactants. So this right here is going to be our whole, and because we want the percentage of each one, we're going to do 2% calculations. The percent magnesium is going to be the part over the whole for the magnesium. Well, again, the part of the Mg, that's 9.03 grams divided by the 12.51 grams, then multiplied by 100. We do that math out, we get that it's 72.2% magnesium. And then likewise for the percent of the nitrogen, same thing. We want to do the part of the nitrogen divided by the whole of the compound times 100. So we're doing 3.48 grams divided by 12.51 grams times 100, and we get 27.8% nitrogen. And that's percent composition. And there are many different uses of percent comp in chemistry in terms of the formula. So we're going to be practicing this in class.